also set our location on planet Earth. So without further delay, so please, Mr. Abdullah, you have the stage, so you can start. Thank you very much. And also let me remind the students that by the end of this lecture, so a chat will open where you have a link to report your name and also your university ID for my students. So please do not use your personal email, use your university ID for me to refer to you. Thank you very much. So please, Abdullah, go ahead.
Thank you, Dr. Yas. Assalamu alaikum. My name is Abdullah Masoud Daria. I am a research assistant with the Space Weather and Ionosphere Laboratory, and my presentation topic today will be a brief introduction to global navigation satellite systems. If at any point during my presentation today my voice is unclear, please let me know, so I'll try to see what I can do. So now the main points that I'll be discussing in my presentation today, or the presentation can be divided into three main stages. First, I'll be talking about some of the history of navigation, the navigation techniques we used before we went to the global navigation satellite system. Then I'll move on to discuss and talk about global navigation satellite systems. And finally, the errors that can be induced in global navigation satellite systems, and particularly our main research topic, which are ionospheric errors. So one of the earlier methods of navigation was known as dead reckoning. And dead reckoning essentially involves estimating your current position based on a previous position. So for that, you would need your speed, time, and direction of travel. Let's take an example. For example, let's say I started at a known position, let's call it start, and I moved northward at a speed of 10 kilometers per hour. 2 hours later, I will be 20 kilometers north of my starting position. So regarding the usage of dead reckoning, one of the first people known to have used dead reckoning is this guy, Christopher Columbus. And in his navigation journal, he detailed, or he spoke a lot about his usage of dead reckoning, particularly as he sailed and navigated to the New World. And during his age, say the 13 to 1400s, the way that dead reckoning would be used is as follows. As we said, for dead reckoning, we require speed, time, direction of travel, and an initial known point. So to find time, especially short periods of time, one would use at that age an hourglass. So this hourglass, as we can see on the right, was designed to measure a single hour, meaning that the sand would completely shift from one point of the hourglass, the top, to the lower point of the hourglass within a single hour. To find the direction of travel at that time, they would have used a magnetic compass, similar to this one, and we are left with speed. Now, the way they would have measured their speed if they were sailing, for example, is as follows. You have a ship, you know the length of the ship, and you throw an object overboard. Because the ship is moving and the object is not, if you are standing on the ship, you'd find that the object shifted a certain distance. This distance, for example, it can be the length of the ship. You would measure how long it took for the object to go from one side of the ship to the other, and then you have time. So the distance, the length of the ship covered in that time would give you the speed approximately. Now, there are some problems with dead reckoning. Since we have a lot of calculations, you have to calculate your speed, your heading, time. Errors in measurement would accumulate over time and would cause significant errors. Let's say, for example, if one is taking a trip from New York to London and he is calculating all these measurements, speed, time, and heading, with 95% accuracy, that'd still be left with 278 kilometers of error, which is very significant. Furthermore, another problem, another issue, would be that for dead reckoning, you require an initial point location. You'd have to know where you started from. So if you are lost, you cannot get unlost using dead reckoning because you have no initial point of reference. Another method of navigation that was popular is celestial navigation. Now, celestial navigation refers to using the sun, stars, moon, and horizon to calculate your position. So for sailors, this was a step up from dead reckoning, especially for long journeys. And Bedouins traveling through the desert would use celestial navigation as well. So essentially, it's useful where you have no known landmarks, so deserts, sand dunes, and oceans. In our region, or let's say in the Northern Hemisphere in general, one of the most important constellations for navigation is the Ursa Minor constellation, known as the Little Dipper, as you can see here. Now, why it's important is because of this star right here. It's Polaris, the North Star. And why it's important is because if you're in the Northern Hemisphere, it can point you towards the north. It appears to be stationary from an observer on the ground, and its elevation from your horizon would equal to your latitude. So let's say we are here in Sharjah at 25.2 degrees latitude. And the elevation of Polaris from the northern horizon is also 25.2 degrees of elevation for us here. So what are the tools of celestial navigation? Well, for celestial navigation, there were several tools. An example would be the astrolabe, and another would be the octant. And one can use them to find the time of day based on the position of the sun, as well as the position of several celestial objects to measure the angle between them and help you position yourself. So what are the issues with celestial navigation? Well, first of all, you'd require to have someone on hand who has considerable knowledge of astronomy. Of course, we can't have Dr. Ilyas with us always because he's busy. And therefore, another alternative will be an almanac, a table consisting of the list of objects and the time that they can be viewed. However, a common person cannot interpret these tables very easily. And we come to the third and most important issue faced in celestial navigation is visibility. Clouds, fog, pollution, be it light pollution or air pollution, would significantly limit our ability to conduct navigation using celestial navigation. And something here to mention is that even though we mentioned these issues, celestial navigation is still used in modern times. For example, it was used by the Apollo astronauts to navigate their way to the moon and back. And satellites nowadays have a component called a star tracker, which helps the satellite orient itself as well as determine its location. And the way it works essentially is that a star tracker is a camera, takes a picture of the sky, and then there's a software that will compare the stars observed within the image with a catalog of known stars, and therefore will help the satellite orient itself. Now, taking an example, for example, this here on the right is the payload of, or part of the payload of the Sharjah Sat-1, which is the CubeSat, upcoming CubeSat of the Sharjah Academy for Astronomy and Space Sciences. And the highlighted in the red box component is the star tracker with its lens covered at this stage. Another interesting fact is that the US Naval Academy reinstated training in celestial navigation in 2016, even though they discontinued it in 1996. And that is because they think it should serve as a backup once the electronic, or if the electronic systems fail. So in the early 1900s, going to 30s and 40s, aviation took off. A lot of people started traveling large distances, airplanes became bigger, airliners carried more people, and during that time, pilots used a combination of dead reckoning and celestial navigation. So what they would do is that during the daytime, they would observe landmarks, for example, roads, and they would use stars during the night. So one of the tools they had was called an astrodome, for example, as we can see on the right image. This is a B-17 bomber, 1939, and it is a transparent semi-sphere that is used by a navigator to be able to navigate using celestial navigation. Now, of course, because of the use of the reckoning and celestial navigation, there were a lot of accidents and fatalities. So people were looking into a more accurate navigation system. And that's how we came upon radio navigation. Now, radio navigation started, or one of the first radio navigation techniques was LORAN, stands for Long Range Navigation System. It was developed by MIT during the early years of World War II, and its main purpose was to provide the US Air Force with a reliable, long-range, accurate, or semi-accurate navigation system. And the system works as follows. You have several base stations on the ground transmitting radio signals. We have an antenna of one, as can be seen here. And the receiver would receive multiple signals, and it would use two of these signals to be able to find the time of arrival, and based on that, locate the user. Now, in the 1940s, the first LORAN system was LORAN-A. It had 300 meters of error and 320 kilometers of range. This was improved by 1974 with the LORAN-C system, which decreased the margin of error tenfold, so from 300 meters to 30 meters, and it improved the range tenfold as well, so from 320 kilometers to 3,200 kilometers of range. It was also available for civilian use in North America, Europe, and Japan. However, it was decommissioned in 2010. So the next step was to look into a more accurate system. But first, let's talk about the issues faced by the LORAN system. So interference and attenuation, because the base station or the transmitters of the LORAN system were ground-based. That means that anything in between the receiver and the transmitter, such as buildings, mountains, would cause significant interference. And also, the area of coverage wasn't great, because you'd have to have a station near every region where you have to have the area of coverage. The stations, of course, are stationary. They don't move. So you'd need more stations to cover a larger area of land. Also, the accuracy, well, LORAN-C was able to reach 30 meters of accuracy, but still 30 meters are not great for specific applications such as aviation. And so people were looking into more accurate methods and more reliable and efficient methods of radio navigation. Then came Sputnik 1 in 1957, the first satellite to be released, and it was released and launched by the Soviet Union. And essentially what it was a radio beacon that would transmit a radio signal, and it was received at Earth. So then people started thinking, what if we use the LORAN system, but instead of having it be stationary on the ground, place it in the sky? And that's how GPS, the first global navigation satellite system, was born. So initially it was known as Navstar, which is short for Navigation System with Timing and Ranging. And the first satellite was launched in 1978. It was commissioned by the United States Department of Defense. And it was only available initially for military use, but in 1983, it was extended to civilian use. The constellation itself was designed to maintain a number of 24 satellites, and it became fully operational in 1993. And the reason why they chose 24 satellites is with that number, it ensures that users can view at least 4 satellites from any point on Earth. I have a picture here of the latest GPS satellite model, which is the GPS-3 manufactured by Lockheed Martin. And as you can see, the GPS satellites are not small satellites, they are considerably large. So there are 4 major global navigation satellite systems, and GPS is the first. But before I go to the other three, I would like to talk about what is global navigation satellite systems. So global navigation satellite system would consist of three main segments. We have the space segments, which are the GNSS satellites. We have the user segment, which are the users, be it drones, cars, us using it, using our phones for Google Maps, for example. And then we have the control segments, which ensures that the GNSS system operates efficiently and adequately. Now, so the way that GNSS works, first you have the satellites. Satellites orbit the Earth, and they know their orbit and time very, very, very accurately. This is very important. The ground-based control stations will adjust this orbit and time when they observe any errors. Then the satellites would transmit a signal, they would broadcast it, and the signal would mainly consist of the satellite's position and the time of transmission. The signal will then travel through the atmosphere until it reaches to the receiver. The receiver then would calculate how long it took for the signal to travel from the satellite to it, since the satellite sends the time that the signal was transmitted and the receiver has the time that the signal was received. Therefore, the time of propagation is known by the receiver, and the receiver can view multiple satellites at the same time. Using this information, the receiver is able to calculate or find the user's position. And this position is sent to different applications as we use, for example, Google Maps and so on. So let me explain how the navigation is done with an example. I'll take here an example of a 2D system. So as I mentioned, the satellite transmits, importantly, two things: the location, its location, and the time of transmission. Also transmits its ID, so the user would know which satellite transmitted what exactly. And the receiver knows the current time. So let's say the receiver received a signal from satellite. Let's call it satellite A. And the satellite told the receiver its location and the time it transmitted the signal. So then we can use an equation, a simple equation. The distance between the satellite and the receiver is equal to the speed of propagation of the signal multiplied by the time of propagation. And the speed can be is the speed of light. The time of propagation is the time of reception minus the time of transmission. So using this, we are able to find the range between the satellite and the receiver, and we find it by drawing a circle. This means that the user can be anywhere on this circle. This is what we get from a single satellite. Then we receive signals from another satellite in a different location. And this is the same information, its position and the time of transmission. So we draw another circle. So we can be somewhere on this circle as well. But now we have information from two satellites. Therefore, we find the intersection between both of these circles, because this will satisfy both conditions of both satellites. And we have two possible locations at this stage from two satellites. So we are not sure if we are either at the top position or the bottom position. And therefore, I use the third satellite and I conduct the same procedure. And therefore, I'm able to find that the intersection between all three circles would be a single point, and this is the location of the user. So this was a 2D system. However, in the real world, we are using a 3D system. It's the same procedure, but instead of using a circle, we have here a sphere, a hollow sphere. So we start with the first step. We receive a signal from the first satellite, and we can represent it by this sphere. Then we receive from another satellite, satellite 2, and the intersection of both of these spheres, hollow spheres, will be a circle. We can be anywhere on this circle, and therefore we use a signal from a third satellite, which narrows down the position to 2 points, the intersection of these 3 spheres. Now, in an ideal world with no errors, no issues, we would look at these 2 points, and one of these 2 points would be unrealistic. It would either be too far into space or too deep into the ground. However, because of errors, you can never be too unsure, and therefore you can never be too sure, sorry. And therefore you use a fourth satellite to narrow down the position and select one of these 2. And that is why 4 satellites are needed for navigation. And that is why all global navigation satellite systems are basing their number of satellites operated on 24 satellites, so that 4 satellites can be available to a single receiver at any point in time, at least the 4 satellites. Okay, so I talked about GPS, and now I'll move to the other global navigation satellite systems. The other is GLONASS, and that's short for Global Navigation Satellite System. And it was developed by the Soviet Union initially as an experimental military communication satellite during the 1970s. But the first GLONASS satellite was received or was launched in 1982, and 24 satellites, a full constellation, was completed in 1995. Here we have the picture of one of the most recent GLONASS satellite models. This is a GLONASS K satellite. Then we go to Galileo. In addition to GPS and GLONASS, there is Galileo. Now, Galileo was commissioned by the European Union, and it started its early operation in December 2016, very recent. And we are expecting it to reach its full operational capability in 2022. Now, unlike GPS and GLONASS, which are at the end of the day military systems, and their main priority is for military objectives, Galileo is intended primarily for civilian use. And according to the European Space Agency, it is controlled by civilians. And once it's fully operational, 2022, the European Space Agency claims that it will be the most precise GNSS constellation, more precise than GPS and GLONASS, with errors expected to be less than 1 meter. This is one of the Galileo satellites. This is going to be the antenna of the satellite to transmit the GNSS signal. Finally, the fourth and the last of the major global navigation satellite system constellations is BeiDou. Now, BeiDou started off as a Chinese regional navigation system in 2000, and the word BeiDou means in the common Chinese, or stands for Ursa Major, or the Big Dipper constellation. And it started providing global coverage in December 2018, which is very, very recent. What's different about BeiDou is that GPS, GLONASS, and Galileo have their satellites only in mid-Earth orbits, all 24 satellites. However, BeiDou has 24 satellites in mid-Earth orbit. It also has 3 satellites in geostationary orbits and 3 other satellites in inclined geostationary orbits. We have here a picture, a 3D model of BeiDou. I couldn't find a picture of the satellite in development, unfortunately. So, global navigation satellite systems face some errors that degrade the positioning accuracy. The most severe of them, we can say, are satellite clocks, orbit errors, and ionospheric delays. And I'll talk about these in detail. So starting with satellite clocks, GNSS satellites have very accurate atomic clocks. That is because time in GNSS satellites is it has to be very, very accurate for the user to find their position accurately. And therefore they use something like this hydrogen measure, similar to what is used in Galileo satellites. And the thing is that these atomic clocks drift by a very, very small amount every now and then. But even this small amount can cause significant inaccuracies in finding the user's position. For example, 10 nanoseconds of clock errors results in 3 meters of position errors. And so what happens is that the ground segment, the ground control segment, who have more accurate atomic clocks will compare their clocks to the ones on the GNSS satellites. And if they notice that there is any discrepancy, they will modify the clocks on the satellites to remove this error. Another issue is orbit errors. Of course, the GNSS satellite must know its exact position, therefore it travels in very precise orbits. However, the orbits drift just like the satellite clocks, and it also has to be addressed because it causes significant errors in the positioning, just like the clock errors. And the orbit errors can be fixed by the ground station or the ground segment. Another issue faced is multipath. So as we mentioned, that to find the user's position, you'd have to measure the propagation time or the time that the signal traveled from the satellite to the receiver, multiply that by the speed of propagation. So if the signal transmitted is not, or the signal received was not actually the signal transmitted from the satellite directly to the receiver, but a reflected version of that, which was reflected off a building, let's say, that means the signal took longer to arrive, and therefore the position would have some errors. The simplest way to eliminate this would be to either set a threshold. So let's say the receiver will not receive any GNSS signals that are less than 30 degrees of elevation. Otherwise, you can move the antenna or the receiver to somewhere that does not have a lot of reflections. For example, in urban regions with a lot of buildings or in mountainous regions. On the other hand, there are some times where you can't move the receiver and it can't be helped. And therefore, typically the design of GNSS receivers as well as the GNSS antennas are done in a way that tries to minimize this multipath errors. Then we come to the tropospheric delay. So the troposphere is a layer of the Earth's atmosphere. It goes up to 15 to 20 kilometers, and it's where most of the Earth's weather takes place. So you have changes in humidity, temperature, and pressure. And because of that, there will be errors added to the GNSS signal. And the way that the GNSS receiver is able to compensate for these errors would be to have a tropospheric model that tries to estimate the error component of the troposphere on the signal and try to compensate for that. And finally, we come to the most significant of these errors, and actually the error that we at the Ionosphere and Space Weather Laboratory actually consider as one of our main topics of research is the ionospheric delay. And so the ionosphere is a region of the Earth's atmosphere between 50 to 1,000 kilometers above the Earth's surface. And in the ionosphere, the gas molecules are ionized by solar radiation. And so we have a layer of free electrons, and that's essentially what the ionosphere is, a layer of free electrons. So when we have the signal traveling from the satellite through the ionosphere and experiencing this high density of electrons, the signals will be refracted, and the refracted signal will take a longer time to arrive as compared to a direct signal. So the way that we at the Ionosphere Laboratory study this is, as I mentioned, we have the refraction of the GNSS signals because of the electrons within the ionosphere. So we study the total electron content, which is represented by the number of electrons which are present between a transmitter and the receiver, as you can see here in the figure. More electrons equals to the worse radio signal is affected. And we measure the total electron content in electrons per meter squared. The equation for measuring it is, as you can see here, the total electron content is equal to 1/40.3. And to be able to measure the total electron content, we have to consider observations from GNSS satellites. And we do this by taking observations from multiple frequencies from the same satellites. Of course, GNSS satellites each satellite transmits at more than one frequency. So we take frequency 1 and frequency 2, and we insert them into the equation. We then find the location or the range between the transmitter and the receiver, just like the equation I mentioned. So the speed multiplied by the time to find the pseudo range, and this can be presented by P2 and P1 from both frequencies. So we use both frequencies, the values, and the range between the satellite and the receiver. And with that, we are able to find the TEC And we can represent the error of the ionosphere, the component of error of the ionosphere, with this equation, where we have 40.3 multiplied by the total electron content, which we found in the earlier equation, divided by the frequency at which you want to observe the error. So if you want to observe the error at L1, you can use the frequency of L1, which is one of the frequencies at which GNSS satellites transmit. So to explain how much of an error we receive, we actually conducted a study in 2018. We used data from a nearby station. The station is in Bahrain. And we wanted to study the effect of the solar cycle, the varying solar cycle, which is a period of 11 years, from 1998 to 2009, on the ionospheric range errors. So in blue, you'll find the number of sunspots. The higher the number of sunspots, the more active the sun is. And on the left, you'll find in red the ionospheric range errors. We have here two trends for ionospheric range errors. We have the upper dotted line, as you can see here, and the lower solid line. The dotted line are the ionospheric range errors estimated by an ionospheric model, similar to models that would have been used by the receiver. And here we used the NECWIC model. Now, it's important to note that a version of the NECWIC model is used by GLONASS satellites to be able to compensate for ionospheric errors. And as we can see, the errors as the solar cycle progresses increase. They can reach up to 20 meters. Now, 20 meters of errors are only because of the ionosphere. That's why we say it's the largest source of error. However, what's important to note here is that the ionospheric model, NECWIC, overestimated these errors. Now, overestimating is not a good thing. It's actually a bad thing. So this means that the receivers near our region would have experienced significant errors of navigation only based on the ionosphere. Now, the total electron content is not the only issue we face because of the ionosphere. Actually, there's another feature which we can call as ionospheric scintillation. And ionospheric scintillation is the rapid fluctuation of radio waves caused by ionospheric irregularities. Irregularities, I mean shapes, irregularities in electron density, as you can see on the right figure. With the elevation, electron density is not constant. It changes, it fluctuates. Some regions have higher density than others. And what it causes is something called amplitude scintillation. When the signal passes through an irregularity, the amplitude would vary, the signal power would change, and the phase might change, the phase of the signal. So unlike the total electron content and the electrons, they induce errors in terms of meters. What the scintillation does, it is completely prevents a receiver from locking onto the signal. And therefore, the receiver will not be able to find their position. And so this is also one of the things that we study. We conducted a study for 2018, 19, and 20 using this time data from our receiver, our own receiver here at the Sharjah Academy. And we found out that at the winter solstice, all winter solstices, we observed a peak of ionospheric scintillation, as you can see here. And this peak starts around 15 local time, that's equal to 3 p.m., up to 17 local time, which is equal to 5 p.m. So for 2 hours. And this period, if you notice, is before sunset. Now, what's interesting about this is that typically what other receivers observe is that there is a peak after sunset up to midnight. However, this is not what we observe. We observe a peak before sunset, and this is something to consider. Looking at it in a map, we can see here we have maps of 2018, 19, 20 rows, and then we have here each map is considered as a 30-minute map. As the time goes by from 15 to 17 p.m. local time, you see that the density of the amplitude scintillation increases. Here, the values correspond to the amplitude scintillation index. The higher it is, the worse the scintillation. And most of the scintillation, of course, can be observed around the edges of the map. And that is because at low elevation, the signal is subject to more irregularities than a signal that's directly overhead. But still, during the peak at around 1530 to 1630, we observe that there is a high density of irregularities at high elevation. And we can even represent this more with this figure. We have here the ionospheric or the amplitude scintillation for 2018, 19, and 20. And we look at it here in terms of azimuth and elevation angles. Most of the occurrences, which are here colored as in percentages from 0% to 100%, are around the edges at low elevation, so 15 to 25 degrees, which is expected. But we observed some pockets of irregularities towards the north and the east of the receiver, which is not expected. Something that we should note here is that these irregularities were observed during a solar minimum period. At this period, we are not supposed to observe almost anything. So this is something that we found to be really, really interesting. So this was amplitude scintillation, meaning variations or considerable variations in global navigation satellite system signals amplitude or power. Another thing we considered was also phase scintillation. So using our receivers, we conducted a study from 2019 to 2021, a period of 3 years, also during a solar minimum for 4 constellations. We have at the top left G, which is corresponding to GPS satellites from G01. At the top right, we have the Galileo satellites from E01 to E36. At the bottom left, we have the GLONASS satellites from R01 to R24. And at the bottom right, we have the BeiDou, the Chinese global navigation satellite system from C2 to C37. And this is the phase scintillation. 0 represents no scintillation, 0.15 represents moderate scintillation, and 0.3 represents severe scintillation. Now, since this is a period of low solar activity, we expected not to see anything from any of the constellations. However, as you can see here, GPS top left and Galileo top right, as well as BeiDou bottom right, showed no variation in phase scintillation as expected. However, the GLONASS constellation, the Russian constellation, showed significant variation. We had peaks for several of the satellites, and that means that these satellites would cause issues during navigation. And this is something we reported in a recent submitted paper. So these are the parameters that we study here at the lab. Since I mentioned what are the issues of each navigation techniques of the reckoning of celestial navigation, it's only fair that I mention what are the issues with GNSS. So because the signal from GNSS are weak, the signal travels a long distance, even when you go through a tunnel or if you are indoors, you will notice that you will receive virtually no signal from GNSS satellites. This makes them very susceptible to interference and jamming, intentional or otherwise. It's also, there is the issue of GNSS spoofing, and that would mean that someone would transmit a signal to look like a GNSS signal, and the GNSS receiver would not be able to differentiate between it and the real signal, and therefore it would give you the wrong position. And this was, this will be a very serious issue. Another would be, well, a GNSS system has satellites in the name, so we rely on satellites, and relying purely on satellites is not a really great idea because there are a lot of issues. You can have the issues of anti-satellite weapons. If a nation chooses, they can shoot down the GNSS satellites of another nation, as was demonstrated by the recent Russian test. Another issue is space debris. There's a lot of space debris, and some of these objects might be able to knock some of these satellites off. Another issue as well would be solar storms, as very severe geomagnetic solar storm would cause significant damage to GNSS systems, even possibly completely knocking them out of use. And therefore, to conclude, if I can say anything, it's good to know celestial navigation in case we need it in the future to use as backup. I'll end this presentation with this picture here. We have the GNSS receiver that we use, or sorry, the GNSS antenna of the receiver that we use here at the Sharjah Academy. If you have any questions, I'll be happy to answer. Thank you.
Thank you very much, Abdullah, for this very nice presentation with all the details and so on. And as we say, so returning to the roots using stars will be much safer than using satellite. But we live by satellites today, so we have to live by, and we have to use all the means to be able to get ourselves. Okay, so let me open the floor. So please, do you have any questions? You can write it in the chat, or you can just ask it verbally. So please go ahead. Any questions?
Assalamu alaikum, Dr. Ilyas.
Alaikum assalam. Please go ahead.
Yes, I am in the planetarium inside. I don't know if you can hear me.
Yes, Muhammad, go ahead.
Yes, please. I want to know if there is any relation between the change of climate and the increasing of the sunspot. Some scientists, they say that when we have an increasing in the sunspot, we are going to the glaciation climate. Some others, they said no, if we have less than this, we have to the hot climate. What is the reality really? Is there any relation between these things, hot, dark spot and the climate? And where is the reality exactly?
I don't think I'm qualified to answer this. Maybe Dr. Ilyas or Dr. Bashir.
Okay, so let me answer this. Thank you, Muhammad Hani, and thank you, Abdullah. You know, between 1650 to 1715, so the 17th and 18th century, the number of sunspots was so small. We call that the Maunder minimum. And during the same period, Earth has lived what you call a little ice age. So it was like a frozen planet. The Northern Sea, north of France, became a frozen sea. The longest river in China, Yangtze, became a frozen river. The Arctic and the Antarctic circles were very close to the Earth equator. So people have linked this little ice age that Earth has passed through during this 1650 to 1715 to the number of sunspots. Because during this period, the number of sunspots were very, very minimum. But there are some new research that have doubts about this sunspot measurement. They said these sunspot measurements were not very well calibrated. That's why they say there is no relation between the number of sunspots if it is low and the weather on Earth or the climate on Earth. So it is the subject that is still under study, under research. As far as I know, there is no direct proof that the number of sunspots will affect Earth weather, will affect your cloud, will affect your rain, will affect it is a study that it's still under research. That's why anything. So you know, in research you need to have a proof, observational proofs, and the measurement that you do are very, very important. So this is what I can say about it.
Thank you, Dr. Shukran.
You're welcome. Any more questions, please? I believe your lecture was so clear, Abdullah, that no one is asking questions.
I had a doctor once say that if nobody asks questions, it's one of two situations. Either they understood everything or nothing. I hope it's the former.
No, we did. Well, no, I believe we have one comment that one student was saying that your lecture was very, very beneficial to them. It was very, very explicit, so it was very easy to follow.
Yeah, that's my job. I hope someone learned something.
Yes. Yeah, we learn a lot. Believe me, we learn a lot. So we are not our knowledge does increase day after day. So okay, so since there are no questions, so thank you very much, Abdullah, for this very, very nice lecture. And okay, there's someone, can I have a copy of your presentation, please? So the student is asking if he can presentation. So Let me just write the number so that I will not forget. You can write it down, Abdullah. You can see the chat.
Yeah.
You can write the number and send him your presentation if you want.
Sure.
Okay, so thank you very much. Thank you for all who have attended, students, research assistant, faculty members. This is very, very important to organize this kind of lectures from week to week. And we still have one last lecture, hopefully, I believe, to be by December 22, and the title is Terraforming Mars. So we need to go to Mars and transform it so that at least we can survive without any proper suit. Thank you very much, and see you in about 2 weeks. Assalamu alaikum.
Wa alaikum assalam. Shukran.